So let's start the session. So this is the session for Blink memory reduction. So this is Hara speaking. But all the data in this slide are collected by the super hard work of Bashi, Tasak, and Hajime Hoshi in Tokyo. So this is a list of projects the memory team in Tokyo are doing. So oil pan, memory reduction, and tab resource reclaiming. And this presentation is about the memory reduction. So Hara-ken, Bashi, Hajime Hoshi, and Tasak are working in Tokyo and closely working with Premiano, SSID, and Ruda in London. So this is a quick history of the project. So as of June, memory reduction was raised as one of the top priorities of the web platform team. So at that point, no one knew even what percentages of renderer's memory is consumed by Blink. So since then, we have been working on understanding Blink's memory and identifying sweet spots to reduce it. So basically, this is the strategy for the memory reduction we are doing. So tooling, understanding, and reducing. So the step one is tooling. So we are building up memory infra and provide consistent data to break down the renderer's memory into pieces. And we are also working on providing reproducible telemetry benchmarks and metrics with which developers can keep track of their reduction efforts. The second step is understanding. So using the tools, memory infra, we are identifying sweet spots that need reduction. And the step three is reducing. So we are brainstorming ideas with the team who own the code base. For example, the loading team is on resources, so we are working with the loading team to reduce memory of resources. And our goal is to enable the teams to get involved in the reduction efforts. So getting more teams involved is a key to have a bigger impact. So that way we can move faster. So this is the agenda of this talk. So the first step is tooling, provide consistent data, and provide reproducible benchmarks and metrics. And the second part is understanding, so identifying sweet spots. And the third part is reducing, so brainstorm ideas and enabling more teams to get involved. So the first part is tooling. So regarding tooling, the first accomplishment is allocator unification. So as of June, Blink mixed 4 memory allocators: partition alloc, oil pan, TC alloc, and system allocators. So it was just crazy. So we removed TC alloc and system allocators from Blink. So currently, all allocators in Blink are unified into partition alloc and oil pan. So here is one question. Why did we remove TC alloc and system allocators only from Blink? So actually, we experimented with unifying all allocators in Chromium with partition alloc, but we couldn't confirm any clear performance or memory win of doing the unification. So some benchmarks got better, but some benchmarks got worse. So we decided to do the replacement only in Blink at the moment. So maybe in the future, we want to do the unification in Chromium, but at the moment, I'm not sure. And another thing is memory infra. So Premiano is going to give a session about memory infra tomorrow. So this is very quick overview. So the London team supported partition alloc and oil pan in memory infra. And we can visualize the very detailed profiling of what Blink is doing in memory infra. And we are also adding more detailed profiling information to get more understanding. So what is the more detailed profiling information? So there are a bunch of ideas. So the first one is what types of objects and how many objects are allocated in Blink. So for example, so in this case, 3 vectors of type rule data is allocated and it is using 12 megabytes, for example. So this kind of information is going to be added to memory infra very soon. And another important profiling information is where large objects are allocated. So when we want to reduce memories, it is important to understand what allocated that object. So in this case, there is a big string, so 1 megabyte of string, and we can visualize the stack trace. So this string is allocated from atomic string, and it is allocated from script resource script. So by this information, we can understand that this string is JavaScript source code. So this way, memory infra is going to display where large objects are located using the stack trace. And the third information is retaining relationships that cross allocator boundaries. So actually, so Blink retains a lot of memory in other allocators in the renderer process. So for example, so HTML link element M resource is holding a pointer to locked discardable memory. So for example, 600 kilobytes. And also font custom platform data M typeface. So this is retaining memory in Skier. So that way, it is important to understand the retaining relationships that cross allocator boundaries. So this is the roadmap for Q4 and Q1 regarding tooling. So we are planning to add more profiling information to memory infra, which is per object type profiler, allocation size profiler, and cross allocator retaining relationships. And also, we are planning to add reproducible telemetry benchmarks and metrics with which developers can keep track of their reduction efforts with confidence. So the second part is understanding. So first, I want to clarify the scope of this project. So basically, our scope is to understand the breakdown of renderer's memory. So from now, I will explain a lot profiling results about Blink, but basically our scope is to understand and reduce renderer's memory, not limited to Blink. So especially we are interested in renderer's memory retained by Blink, but anyways, our scope is to understand and reduce renderer's memory. So another important question when considering scope is, so should we focus on short-lived apps or long-lived apps? So for short-lived apps, memory after 10 seconds after a page load matters. So on the other hand, for long-lived apps, memory after 1 hour after a page load or a lot of user interactions matters. So at the moment, we are now focusing on short-lived apps because short-lived apps would be more important in mobile devices, but long-lived apps are also on our radar. So what do we want to do? So we want to break down the entire memory into pieces. So break down the renderer's memory into V8, partition alloc, oil pan, skier, discardable, TC malloc, and a bunch. And after that, to understand what Blink is doing, so we want to break down the partition alloc memory into each partition. So partition is a notion in the partition alloc to separate object types into multiple partitions. So buffer partition, first malloc partition, node partition, and layout partition. So I will explain the details later. And after understanding the breakdown of each partition, so we want to break down each partition into per object memory. So for example, in case of buffer partition, so it contains strings, vectors, hash tables. So what's the breakdown? So this is what we want to understand. So this is the latest result of the breakdown of the renderer's memory. So this is a list of key 10 pages where Blink's memory reduction is a key. So the interesting observation is, in common cases, V8 is the largest memory consumer. So however, in these websites, partition alloc is the largest consumer. So this is just because we chose the page set in a way that where Blink's memory reduction is a key. So because these page sets are chosen where Blink's memory reduction is a key, so partition alloc is consuming the most memory in these pages. So it is consuming from 20% to 40% of the renderer's memory. So V8 is the second largest memory consumer. So in summary, in common cases, it is true that V8 is the largest consumer, but in these pages, Blink is the largest consumer. So the important fact is Blink can be the largest consumer in popular websites. So in these cases, Blink is consuming from 20 to 40% of the renderer's memory. And also, the important fact is some of the memory in discardable CC and Skier is retained by Blink. So CC, discardable Skier are consuming a bunch of memory, but some of them, so I'm not sure how much, but they are retained by Blink. So it is important to understand the retaining relationship. So this is BlinkOn, so it's important to understand what Blink is doing. So because we have not yet fully shipped oil pan, so most Blink objects are currently allocated in partition alloc. And as I mentioned, partition alloc has 4 partitions: node, layout, buffer, and fast malloc. The node partition contains node objects, and the layout partition contains layout objects. And the buffer partition contains vectors, hash tables, string inputs, and array buffers. And the fast malloc partition contains shared buffers, which is a backing storage for resources and all other normal DOM objects. So let's break down the partition alloc memory into these partitions. So this is the result. So this is the 10 pages and the buffer partition, fast malloc partition, node partition, and layout partition. So as you can see, the buffer partition is the largest consumer, and the fast malloc partition is the second largest consumer. And the node partition and the layout partition are not using large memory. So in summary, the largest consumer is the buffer partition, which contains string inputs, vectors, hash tables, and array buffers. And the second largest consumer is the fast malloc partition, the shared buffers, and all the objects except for nodes and layout objects. And also, size of node and size of layout objects don't really matter for the total renderer's memory. So next, let's understand the breakdown of the buffer partition and the fast malloc partition. So this is the breakdown of the buffer partition. So string inputs, vectors, hash tables, and others. So as you can see, string inputs is the largest memory consumer, and vectors and hash tables follow. So the largest consumer is string inputs, and we confirmed that more than 90% of the large string inputs, so larger than 50 kilobytes, are JavaScript source code. And also the second largest consumer is vectors and hash tables. And we confirmed that 25% of the vectors are consumed by the unused region between size and capacity. So this makes sense because the expansion factor of vector is 1.25. So 25% of vectors are consumed by the trailing unused region. And also we confirmed that 70% of the hash tables are consumed by the unused region of small hash tables. So actually, the initial capacity of a hash table is 8. And normally, only 1 element is stored in that hash table. So 7 elements are wasted. So it is increasing that wasteful number. So this is the breakdown of the fast malloc partition. So shared buffers and all other DOM objects. So as you can see, the largest consumer is shared buffers and a bunch in other objects. So in summary, the largest consumer in the fast malloc partition is shared buffers. So they are used as backing storage of resources. And other objects have a very long tail. So actually, the second to fifth largest consumers totally depend on web pages. And this means that reducing size of DOM objects won't contribute to reducing renderer's memory. So okay, so this is the summary. So the largest consumers inside Blink are string inputs, shared buffers, and vectors and hash tables. So here is an important question. So by the way, so how much memory is consumed by vectors and hash tables as absolute values. Yes, it's only less than 1 megabyte. So even in the Blink heavy pages. So this means that it's not worth reducing. So what does it mean? So inside Blink, the only objects we should really reduce would be string inputs and shared buffers. And reducing other objects won't contribute to reducing renderer's memory. So this is our current understanding. So our current understanding is after reducing string inputs and shared buffers, we should look at outside Blink, not inside Blink. So as I mentioned, so even in the Blink heavy pages, outside Blink is consuming 60 to 80% of memory. And also the important fact is outside Blink doesn't mean that Blink is not related. So as I mentioned, Blink retains a bunch of memory in discardable, scale, and CC. And remember that our goal is to reduce renderer's memory. So our current understanding is after reducing these two objects, we are planning to look at outside Blink, especially outside Blink retained by Blink. So this is our current understanding. So I would like to talk about what we have learned in these investigations. So one thing we have learned is memory reduction based on a guess is not likely to contribute to a meaningful reduction. So for example, we have invested a bunch of efforts to reduce size of node or size of CSS values. So however, so actually reducing size of DOM objects won't have an impact. And also, we experimented with discarding various Blink caches, each TL listed in this spreadsheet. And Bashi experimented with discarding these items one by one, but most of them didn't have an impact. So reduction based on a guess won't work. So it is important to drive the reduction efforts more tactically. So understand the breakdown and identify key problem areas and reduce the memory at a pinpoint. And another thing we have learned is it is really, really hard to collect consistent and reproducible results. So for example, it is a substantial amount of work to confirm the reasonableness of various memory metrics. So for example, currently we are collecting the memory usage of each allocator, discardable, scarce, CC, partition alloc, oil pan. However, it never matches the renderer's private memory OS reports. So where does the dark matter come from? This has been one big question. And we solved this problem 95%, but not 100%. And also there are various notions about sizes. So resident size, effective size, active size, committed size. So it's very, very confusing. And it's a substantial amount of work to confirm the reasonableness of these memory metrics and correct, consistent values. So this is what we learned, and we are working on improving the accuracy. So regarding the understanding part, so this is the roadmap we are considering for Q4 and Q1. So the first one is get more understanding on outside Blink. And also, we want to understand the real world. So UMS, deep reports, and what's going on in OOM. And also based on these understandings, we want to identify 3 or 4 projects that would have the biggest impact on reducing renderer's memory. And also profiling long-running apps is on our radar. Okay, so the final part is reducing. So as I mentioned, so our strategy is provide good tooling and understanding and brainstorming ideas for reduction and enable more teams to get involved in the reduction. So instead of only the memory team working on the reduction, so that way we can move faster. So this is our strategy. So a bunch of projects are going on. So this is a list of the ongoing reduction projects. So memory purge controller, compressible string, and more aggressive resource pruning, and making V8 Blink cycles collectible. So I will take a look one by one quickly. So the first one is memory purge controller. So basically, so when Blink should save memory, so memory purge controller dispatches purge memory. So memory purge controller, and there are a bunch of clients of the memory purge controller. So for example, in this case, memory cache is made as the client of the memory purge controller. And when Blink should save memory, so purge memory is dispatched in the memory purge controller. So the client just needs to implement the purge memory. So in this memory cache case, we can just prune all resources, for example. So we want to increase the number of clients of the memory purge controller so that we can purge more memory when Blink is in our memory pressure scenarios. So the key question here is, when does memory purge controller dispatch the purge memory? So currently, purge memory is dispatched in two scenarios. So the first scenario is 10 seconds have passed after a tab goes inactive. And the second scenario is when Blink receives memory pressure listeners moderate or urgent notifications. So it's not that common. So it's basically so only when the tab goes to inactive or the tab is really in a memory pressure scenario. The next key question is, what should the purge memory do? So basically what we are currently doing is discardable caches in Blink. So basically, in August, I asked HTL to list up caches in Blink that are potentially discardable. And it's not a good idea to randomly discard these caches because it affects performance. So we are very careful about adding items to purge memory, but we are investigating performance and its memory impact. And if we think it's worth doing, so we are adding that item to purge memory and implementing the purge memory from the memory purge controller. So as I mentioned, so the purge memory is dispatched against only inactive tabs and memory pressure scenarios. We must be careful about its performance impact. So the next reducing project is compressible strings. So as I mentioned, the largest consumer of partition alloc is large strings, larger than 50 kilobytes. And we confirmed that more than 90% of the large strings are JavaScript source code. And the observation is that JavaScript source code is not discardable because V8 needs it. So the only option to reduce the memory is to compress the strings. So we are introducing compressible strings and use it for V8 JavaScript source code and CSS text resource and a bunch of things. But usages should be limited. So according to our experiments, we confirmed that if we gzip large strings, we can reduce partitions alloc memory by from 10 to 60%. So 17% in average in these websites. And another thing we are doing is more aggressive resource pruning. So as I mentioned, the second largest consumer of partition alloc is shared buffers. And shared buffers are used as backing storage of resources. So memory reduction of resources is very important. And actually, memory reduction of resources is more important than the data implies because resources also retain memory in discardable and scarce. So some resources use locked memory in discardable, and image font resources can hold caches in scarce, for example. So it is important to understand what resources are retaining and reduce that memory. So here is a bunch of low-hanging fruits. So for example, HTML link element should clear CSS style sheet resource when it finishes parsing the style sheet. So we confirmed that just doing this reduces 1.2 megabytes from Pinterest.com and 800 kilobytes from TheVerge.com. And glyph page should discard glyph page 3. This reduces to 100 kilobytes from TheVerge.com. So there are a bunch of low-hanging fruits. And anyway, so our goal is don't keep alive resource pointers longer than needed, and discard various caches retained by resources, so unless it regresses performance. And finally, we want to visualize the retaining relationship in memory infra so that we can understand what is going on in Blink. So the final reducing project we are currently doing is making V8 Blink cycles collectible. So in common cases, so as you know, V8 is the largest consumer of renderers memory. So at the very least, Blink should not be the culprit of V8 memory leaks. So here is a good example. So consider this code. So E equals new custom event who detail new error. So actually, so this code has been causing a lot of window leaks in real-world Polymer apps. So this is what was going on. So this code creates custom event and custom event wrapper, and there is a left pointer from custom event wrapper to the custom event object. And we are creating detail objects. So this custom event holds a strong V8 persistent handle to the error object. And the interesting observation here is any V8 object is holding a strong reference to the window object that created the V8 object. So there is a strong reference from the error object to the window object. And there is window.e, which is pointing to the custom event wrapper. So there is a cycle that crosses the V8 Blink boundary. So this caused the entire leak of the window object in Polymer apps, and the memory was brought in. So as I mentioned, in general, a V8 object has a strong reference to the window object that created the V8 object. So this means that if a Blink object retains a V8 persistent handle to the V8 object, so it retains the entire window object, which can be huge. So the idea is remove all V8 persistent handles by making V8 Blink cycles collectible. So this is what Johan is going to start. So, but basically, so the problem is the V8 persistent handle from Blink to V8. So let's remove it. So by making this V8 Blink references traceable. So in this idea, V8 garbage collection traces inside Blink and figure out the references that crosses the V8 Blink boundary. So by doing that, V8 persistent is no longer needed, and all V8 leaks caused by Blink will be gone. So anyway, so various reduction projects are going on. So memory purge controller and compressible string and more aggressive resource pruning and making V8 Blink cycles collectible. So as I mentioned, so inside Blink, string inputs and shared buffers are important. And these projects are going to address that problem. And as we identify more key problem areas, we'll work with teams who own the code area and brainstorm more ideas for reduction. So this is a roadmap for Q4 and Q1 regarding reducing. So we want to establish the following development flow. So the memory team provides good tooling and identifies key problem areas and work with teams who own the area and brainstorm reduction ideas. And then enable the teams to set memory reduction OKRs and work on the reduction. So we want to establish the development flow in Q4 and Q1. So conclusions. Our scope is understand and reduce renderers memory, not limited to Blink. And our current understanding is in Blink-heavy pages, Blink can be the largest consumer. So it can consume from 20 to 40% of memory. And the largest consumer is string inputs, shared buffers, and vectors and hash tables. And as I mentioned, the absolute value consumed by vectors and hash tables is ignorable, even in the Blink-heavy pages. So our plan is after reducing string inputs and shared buffers, we should look at outside Blink because some of them are retained by Blink. And our strategy is tooling, understanding, and reducing. So provide consistent data in memory infra and provide reproducible telemetry benchmarks and metrics and identify sweet spots and brainstorming ideas and enable more teams to get involved. So finally, our goal is to establish a development flow that enables each team to set memory reduction OKRs and get involved in the reaction. So I'm planning to empower this effort using the tooling and empowering tooling for that direction. So that's it. Thank you very much. Yes.
Yeah, so it sounds like the main culprit is V8 needing those strings. Is that just because it needs to those when it throws exceptions? Or why does it need to keep the source code?
So V8 needs a string because if toString is called for function, we have to return that string. And also, in the current implementation of V8, V8 needs the JavaScript source code to recompile that code. So V8 can discard JIT code when it discards JIT code, and when it recompiles, it needs JavaScript source code in the current implementation.
Okay.
Okay. So Hannes?
I think one problem we had in the past, and we may still have, is having the right benchmarks for memory. I'm not sure which benchmarks you used, but I'm assuming you used the top 25 benchmarks of telemetry, which basically reflect a happy case for memory, right? They just start out of a fresh renderer, run for a few seconds, and then shut down. I think what would be really nice to have would be like really long-running benchmarks, because they tend to trigger really bad cases, and in these cases, we used to do really bad.
Yes, I totally agree. So currently, we defined key 10 pages where Blink's memory is key, and we are adding those benchmarks to telemetry, but the metrics are not enough. So we are adding more metrics and make it more reproducible. So this is very, very important work. So I totally agree. Yes.
Thanks for the talk. You mentioned this retain relationship towards platform libraries, or into Skia, for example. Can you say a bit more what you're planning to do to sort of uncover what's maybe hidden behind Skia API or behind other APIs?
Yeah, so actually, so I don't know. So, but basically, so for example, so in this case, glyph page is this one. So font custom platform data is caching font faces in Skia. So this is one example. So for example, this kind of relationship and metrics should be added to memory infra so that we can keep track of the reduction. And once we have that, we can understand how much it is, how important it is, and we can just discard it in our memory pressure scenarios. So that's our plan.
Hello, are you able to artificially inflate memory usage on people in the wild and sort of see what that does for a particular area based on user metrics? Right, so one of the things that you end up having is you want to say, okay, for this particular area, if we were able to reduce it by 20%, how much would it actually have for an impact? One way is that you could artificially inflate by 20%. Have you tried sort of things like that to see what the impact is, not just based on benchmark suites, but based on real user?
Yes. So we are adding a bunch of UMAs to understand the memory usage in the real world. So one thing we are going to keep track of is memory purge controller purge memory. And we want to compare the memory usage before calling purge memory and after calling purge memory. So we want to allocate a memory usage from the wild and collect that UMAs and measure how the purge memory actually reduce that memory. So this is one example, but I totally agree with you that we should collect more UMAs to understand real world memory. Yes. Okay, so it's time? Yes. Yeah. Okay, so thank you very much. So any question is welcome. So thank you very much.